Hello all, welcome to this tutorials in which we shall be looking into the extension of the base classifier that we saw during our previous session. While we were considering the base classifier, the assumption was we were dealing with a two case. Okay, we were having two classes. Okay, so and then we were dealing with 0 1 loss. So now we shall go ahead and come up with a much more generic model and try to understand in a generic way the details. So let's go ahead with that. Now let's consider the base classifier with m classes and any loss function. So in our earlier sessions, Professor has explained that he has taken a two-class case with an emphasis towards 0 1 loss. Now we will go ahead with a much more generic approach and then we will look at it. Let's say that y, which is what for practical sake we will be calling it as labels, can take values C0, C1, so on till Cm minus 1. Now these are true labels. Okay. And then we have an hypothesis function which takes x as an input and then gives the prediction or output. They can be alpha 1, 0, alpha 1, so on till alpha k minus 1. Now these are decisions from the hypothesis function. See, here we are looking at a much more generic case. Okay. So here the decision of the hypothesis function can have more labels also. Now, for example, one standard thing that you can think of is a reject case. So wherein which my k will be m plus 1. Okay. So we are looking at a much more generic case now wherein which the labels, the true labels, okay, is a subset of the decisions from the hypothesis function. Okay. So we are considering a generic case in general, the number of outcomes in the number of the cardinality of the true labels is not equal to the number of outcomes from the hypothesis function. So now in this case, how do we define the loss? So the loss is defined as a function from the outcome of the hypothesis function cross y to r plus. Okay, so let's define this. Now let's say that the loss when my hypothesis function says the decision it takes is alpha j, but the actual label is ct. Okay, this is a loss that is incurred. So this is loss when the hypothesis function is saying it's alpha j and true label is ct. So in this particular framework, what happens is Now let's look at the risk of this particular setup now for any classifier. Okay. Now risk of the classifier is RH is equal to the expected loss over the joint XY loss of H of X, comma Y. Okay, this is the risk. Now what do we want? So we want a classifier with the least risk. Okay, we want a classifier with least risk value. Okay, so now let's look at this. We know that the risk for any hypothesis function. Okay, so let's make one more thing here to be more specific. Let's say that we have a class of hypothesis functions for which the H belongs to. Okay, just to make it complete. So now this is expectation with respect to the xy. This is loss of H of X, comma Y. Now this I can decompose into expectation with respect to X into conditional expectation Y given X loss of H of X, comma Y conditioned on X. Okay, so now what we will say, this is the what is known as the conditional risk. This is conditional risk. Okay, so now you can easily see it from here. So now this conditional risk is dependent on my hypothesis function. Okay, so now this you can easily expand it. This is over X. This is, I can come up with conditional risk, okay, given X, and then Px of X dx. Okay, so fine. So now let's try to understand this conditional risk in a comprehensive manner. Okay, so let's go to this conditional risk for a given example X. Okay, consider X. Consider X. So now let's say that classifier H of X is alpha I for this specific case. Now then I can come up with a conditional risk. Okay, now what does it denote? This denotes the expected loss when the classifier says the given example X can be put into alpha I's bucket. Okay. This denotes expected loss when classifier says alpha I for the given X. Okay, this I can actually go ahead and write it as for given X. This is expectation with respect to Y given X. Okay. Now this is loss H of X comma y conditioned on, I have already know that for this given example, my classifier is saying it is alpha I, then conditioned on my input. So now because of this will be again expectation with respect to y given x loss alpha I. No, because I already know that the outcome of my hypothesis is alpha I, comma y conditioned on x equals x. Okay, fine. So now this is y is a discrete random variable. So now we know the expectation of this. This is straightforward, even though it's a function of x. So we can write it as a j is equal to 0 to m minus 1. This is loss. It says into p of y given x when y is Cj for a given input x. Okay, so now a couple of now this y given x is known as the posterior. Okay, now whenever you have p of, okay, let me just make a note of this. Now, whenever p of y given x is known as the posterior, p of y is known as the prior, the distributions, okay, prior distribution, and then p of x given y is class conditional. It's class conditional. Now this is posterior. Okay, so now this is a much more generic view of looking at the risk. So now what do I have? Now let's put things together. Now we have, in general, we have risk when your hypothesis function is giving you certain decision is summation j is equal to 0 to m minus 1 loss incurred. It is giving h of x Cj, and the posterior y given x when y is Cj given x equals a specific example. Okay, so now this you can go ahead and substitute it back. This is the conditional risk. Now this you can go back and put it here. Okay, now this is a much more a generic viewpoint of looking at the risk. So now with this much in hand, now what do you mean by an optimal classifier in this case? Now the x is fixed. Okay, now here, now x is fixed, and then this risk now which is a positive entity or non-negative entity. It can be 0 as well. Okay, so now for the classifier for which this is minimum, this conditional risk is minimum, we are actually in search of that specific classifier. Let's make a note of that. Now therefore, now what do you mean by optimal classifier in this case? Now for each x, h of x should be such that risk when you have incurred should be less than or equal to using risk obtained for any other hypothesis function that belongs to the class of hypothesis functions H. Now, this is what we mean by the optimal classifier in this case. Okay. So now let's bring in the Bayes classifier. Now, the Bayes classifier, let's call it HB for a generic M class is, so my Bayes classifier or Bayes hypothesis function will say alpha I if you look at the conditional risk, which is given by this summation of loss incurred by saying alpha I Cj into the posterior y given x, when it says it is Cj given x, okay, is less than or equal to 0.02 m minus 1 loss incurred when saying it is some class. The decision is alpha t when given x, y equals Cj given x for all t. Now, what is it saying? So the conditional risk which I obtain when my decision is alpha I is less than taking any other decision. Okay, and then so since you have an equality, now how do you break the tie? No, we break the tie arbitrarily. Okay, so always break ties arbitrarily. Okay, now this is the formulation of the hypothesis function using a Bayes classifier in an M class case, in an M class, and even it's for any loss function. Now again, haven't reiterating, I haven't explicitly taken 0, 1 loss. Okay, we will take it as a special case and then we will look at it in some time. Okay, so now just to link it to our earlier case, now let's consider the one that has been looked in our class. Let's consider m is equal to 2. Now, then the outcomes, okay, now that is, see again, when I say m is equal to 2, now y can take values between 0 and 1, or any, there are two outcomes in y, but that doesn't mean to say that what will be the outcome of the hypothesis function. Okay, please keep that in mind. Okay, better we can fix that also. Now, there are only two outcomes that the hypothesis function is also giving, alpha 0 and alpha 1. Now you can fix it. Now else you can sum it over. That's also fine. Now let's fix it 2 in this case. Otherwise, so if the loss incurred when the hypothesis function says it is alpha 0, say 0, into the posterior y given x. Now y equals C0 given x plus, when it says alpha 0, but the actual class is C1, into the posterior y given x is C1. Let's make it clear. Now, in this case, I am assuming that y can take values C0 and C1. Now, h of x takes values alpha 0 and alpha 1. Now, we are making it much more generic. So, you can fix it. So, I just want to, what do you call, drive in the idea that, okay, now these two things can be different. Okay, you can have multiple elements over here. That's totally fine. This is less than loss incurred when you take 0 y given x plus C1, the posterior y given x, y is equal to C1 given x. Okay. So now if you have multiple values that your hypothesis function can take, but then this has to be the least. Now then you represent it by some alpha t here, and then you say that for all t, so that the indexing that is happening for this hypothesis function, you can go ahead with that. Okay. So now let's make it. I know that it is too verbose, having too much of notations. So now let's reduce the notations. So now let's take the 0 1. Now I am coming to the specific case of 0 1 loss. Now consider 0 1 loss. Now what do you mean by that? The loss incurred when I'm saying for 0 and C0 is equal to the loss when I'm saying for 1 and C1, these are same, okay, is 0. Okay. Now this is, I'll just indicate it by 0 0 0 1. Okay, I think that should be comfortable by now. In y also I'll indicate just with by 0 and 1, which makes the notations much more easier to parse. Okay, now by now I assume that all of you are comfortable with the notations, so I can just say that the first value in this loss, as I have defined earlier, now this is the outcome of your hypothesis function. This is the outcome of your this is your true label. Okay, in most of the cases it is y cross y. That's what we have also looked into, but this is a much more a generic way of looking things. Okay, fine. Now let's reduce the burden of notations. Now how it will be? Now loss incurred when my hypothesis function says 0, but the true label is 1, given with that y is equal to 1, given x is less than or equal to loss when 1 0, probability that y is equal to 0, given x. Okay, now this is what it finally boils down to. Okay, much more simpler notations. So why is this? Now because this will be 0 and then this will be 0, therefore you have this term and this term. Now wherein which there is a mismatch in terms of the decision. Now this you can easily rewrite it as a ratio of posteriors y equals to 0 given x divided by the posterior y is equal to 1 given x is greater than or equal to loss incurred, okay, 0 1 1 0. Yeah, this you can look into. Okay, now this is what is known as the ratio of odds, famously known as the ratio of odds. Okay, now let's go back to our M class case. Okay, so now let's go back to our M class case and then try to bring in the notions of much more comfortability there. So now I am generalizing it for a 0, 1 loss in our M class case. Okay, now let's generalize this to an M class case and 0, 1 loss function. Now let me reiterate how will my risk looks like. Now even x equals summation over all the true labels and the loss incurred when I say alpha I, and the true label is Cj, and P of y given x, y equals to Cj given x. Now this I can easily write it as, now this is, okay. Now only when the outcomes are different, the loss is 1. When the outcomes are same, the loss will be 0. That's how the 0, 1 loss works, right? So now only when I and j are different, now then there will be a loss of 1, okay, else it will be 0. Now that means that now this I can easily write to the case now wherein which j not equal to I, for every j that is not equal to I, j taking value between 0 to m minus 1. Now this is that y given x, y is equal to Cj given x. Now this is 1 minus probability of y, the posterior y given x, y is equal to Ci given x. Okay. Now therefore, now how will be my base classifier? Now therefore my base classifier b of x. Now this will give us I1 1 minus y given x, y equals Ci given x is less than or equal to 1 minus posterior for any other j, for any other outcome. This is for all j, for all j that belongs to 0 to m minus 1. Okay. Now this will be y given x, y equals to Ci given x greater than posterior. Now this we know. Okay. Now things are intuitively clear. Now what is this? Now this is, now which one is having the highest probability? That is the one that I am considering, right? Now I will say that my hypothesis function is giving me, I'm assigning this particular label when the probability of that specific case is maximum in all of the true labels. Okay. So now this is the M class classifier for 0, 1 loss function. This is minimizer of the probability of misclassification. This makes Okay. Now that means that for whichever class we have got the highest probability, that is the label that I'm going ahead. Okay. Now this is the thing that was left as a small takeaway in the class. Okay. So now what we shall do is, now we shall delve deep into this, and then we will try to come up with some nice cases that we all know. Okay. So now what we shall do is, now let's take a two class case. Okay. There are two labels. Okay. Now for a two class case, let's let's consider m equals to 2. And then in that case, how will the things looks like? Now the laws incurred 0, 1, and then y is equal to 1 given x. So laws incurred 1, 0, y is equal to 0 given x. Now this, the posterior, now by Bayes rule, now this I can decompose into 0, 1, x given y is equal to 1 into that y is equal to 1 less than laws 1, 0, x given the class conditional into the prior. Now this I can easily write now. So now you'll ask, now what about px? So now you can just cancel it off, right? Okay. Now I think this much of algebra, all of you should be comfortably able to do it. Okay. So now my posterior, which I have, now I can replace it as the product of the class conditional and then the prior. Okay. So now this, I can take log on both sides. Why I'm taking log on both sides is, then what I'll assume is, now for this specific class conditional, I will go ahead and consider it as a Gaussian. Now and then a Gaussian has an exponential, and then you have a log. Both of them will get cancelled out, so that we can get some beautiful forms. That is where I'm heading. For that specific reason, I can take log. I can take log. Okay. Now taking log on both sides, and then we are assuming, x given y. Now the class conditionals be Gaussian distributions. Okay. See here I am taking 1D Gaussian. Now I will leave it as an exercise for you to take so a d-dimensional Gaussian distribution and see how a similar expressions can be obtained. Okay. So conditionals be Gaussian distribution. Okay. So now this I can applying log, I can write it as ln of probability phi is equal to 0 into loss 1 comma 0 plus ln of probability x given y is equal to 0. This has to be less than ln of probability y is equal to 1 loss 0 1 plus ln of property x given y is equal to 1. Okay. Now let's substitute the class conditionals. Now we know that property of x given y is equal to some I. Okay, some I of this x given y is equal to I. This I can write it as 1 over sigma I square root of 2 pi exp of minus x minus mu I whole square divided by 2 sigma I square. Okay, now here I, in this particular case, I can take value 0 and 1. Okay, so now what will happen? Now let's take one case. Okay, let's take a generic I and then substitute it later onto this particular thing. Okay, now let's take the log of this and try to see now how it is. Now if I take the log of this, okay, now this is taking log. Okay, just here, this is ln of 1 over I 1 over square root of 2 pi plus minus x square minus mu I square plus 2x mu I divided by 2 sigma I square. Now this can easily write it as minus log of sigma I minus half into log of 2 pi minus x square divided by 2 sigma I square minus mu I square divided by 2 sigma I square plus 2x mu I divided by 2 sigma I square. Okay, now this is the case. Now I can substitute this, now which is there, now back into this specific equation. Okay, now I'll substitute this. Now you have this term, and then this will be replaced with this. Okay, so now this will be ln of p y equal to 0 is the first term 0, loss of 1 0, this is there, minus ln of alpha 0, oh sorry, sorry, not alpha 0, this is sigma 0 minus half into ln of 2 pi. Okay, a very big term, nice. Okay, now remember the joke that sir made it in the session. So Fermat's last theorem. So this is the correct case that I also have. But anyhow, okay, minus x square divided by 2. Okay, so let's do this. Now I'll leave this whole algebra to you, and then I'll rearrange the terms and write the final equations. Okay, so I assume that you can substitute this, then make that thing. Okay, so you have to substitute in this. See, now think of it like this. Now what is happening? Okay, now you have an x square term, you have an x term. Okay. Now look at, now this is log of something. Now this is, again, this is a constant, no need to worry about this. Okay. Now you have an x square term and then you have an x term. Okay. So now let's take a case how this will affect by the choice of mu and sigma that I take. Okay. That's where I'm going now. Okay. So now by rearranging the terms, just skipping the algebra, just make a note of this. Skipping the substitution, and rearranging the terms. Okay, you rearrange the terms, then what will happen is I will just half x square into 1 over sigma 1 square minus 0 square plus x mu naught divided by naught square minus 1 square. Okay, again plus half mu 1 divided by sigma 1 square minus, sorry, mu 1 square, this is 1 square, plus log of 1 sigma naught plus ln of p y is equal to 0 into loss of 1 0 divided by p y is equal to 1 0 comma 1. This whole term greater than 0. Okay, I'm just shuffling things. So now if you look at this, now you have an x square term, you have an x term, and then you have some bunch of constants put together. Now this is similar to ax square plus bx plus c. Okay, now when you have mu and sigmas fixed, okay, and for sure, yeah, now you take you fix these values and fix the prior probabilities. Once you fix this, now this is a function of your x, is what I am telling. Okay, so now this is of the form. Again, now where I am going, now I am taking a base classifier, now where in which I have a 0 1 loss, and then I have two outcomes. It says 0 if ax square plus bx plus c is greater than 0. Okay. Now what happens is, now this is what is known as a discriminant function, right? Okay. Now this, your base classifier in this case, is nothing but a quadratic discriminant function. Okay. Now, all these algebra that we are trying to do is just to show that, see, now your base classifier, which is there, now is nothing but a quadratic discriminant function, and then we will assume certain specific cases, and then can we reduce it further? We will look at it now. Okay. So now this means, now this implies the base classifier, in this case is a quadratic, in this case a quadratic discriminant function. Okay, this is a quadratic discriminant function. Okay, so now what is that case? Now I'm considering the base classifier, my m is equal to 2, and then I'm considering 0 1 loss, and then I'm assuming that my class conditional is Gaussian with mu 0 and sigma 0. Similarly, mu I, sigma I. Okay, those are the conditions that I have applied on this. Okay, now because of which my base classifier has turned out to be a quadratic discriminant function. Okay, So now what we shall do is, now we will take some special cases of this again. Okay, some special cases. Case 1. Okay, let me make it some special cases. Some special cases. Now case 1, where in which I am saying that sigma 0, sigma 1 is sigma, and then probability that y is equal to 0 is equal to the priors are same, and that means that it's half. Okay, this is half, and then the loss that is incurred in both the cases are same. Now, when I'm saying that the loss that is incurred in both the cases are same, no, that means that there can be cases in which they can be different actually. Now, in that case, what will happen? Okay, now I'm hinting you towards some other ideas. Okay, now just think of it. Now, in this case, I am saying that both the losses that are incurred are same. Now, will it be always like that? Now, that means that whenever now consider your all of you remember the COVID times, right? Now, let's say that 0 is negative and 1 is positive. Now, will the impact when I say that a positive COVID positive person is actually, I say that he is negative, will it be same as when I say a negative person is positive? Can I make that assumption? Is what I'm asking you. Okay, that may not be the case. Now, there are multiple kinds of errors. Now, which error are you looking into? Okay, now look out for that. Now, we will have some more discussions on it. Okay, this is just a small link so that we'll be discussing them again. Okay, yeah, sure. Now coming back to our present case. Okay, now I'm assuming these things. Now then, what will happen? Now then my base classifier is say 0 when, see, now let's put this up and see. Now when this will go off actually. Now when sigma 1 and sigma 0 are same, now this will go off. Fine. Now, then this is a term of x with some constant. Okay. So now let's write it up. Then it will be x, and then this will go off again. This term will go off. This term will go off. Correct? This will go off. This will go off. This will go off. These terms will go off under the current conditions. Okay, x divided by sigma square into mu naught minus mu 1 minus 1 over 2 sigma square naught square minus mu 1 square is greater than 0. Now, without loss of generality, I'm assuming that mu 0 is greater than mu 1. Now, in that case, x is this will be your condition. Assuming mu 1. Okay. Now, this is a linear case. Now, how does it look like? Now, these things I can simulate, right? I know the values of my sigma, I can fix it. I can fix some mu's and then see how they look like. That's what exactly I have done. Okay. Now, this is class 0 and this is class 1. This is your decision boundary. This is your discriminant function. Okay. So we'll be sharing this code. You can look at it, but individually, this is what it is actually. Correct? Now, this is the one. This is a base classifier, and we all know that base classifier is the optimal classifier. Now, what will happen if I move this line here? What will happen if I move this line here? Okay. And then, in those cases, the error is not optimal, right? Okay. I assume that all of you can appreciate this. Okay. Now, this is the base classifier that I have. Now, what are the so the samples that I have generated is mu 0, I have taken it as -1, and mu 1, I have taken it as 1, and then I have done this. Okay. This will be the optimal classifier that I have. So now let's look at another case 2. Case 2 is where I have my mu 0 and mu 1 are 0. My priors are same, they are half, and then the loss are same. Now in this case, now what will happen? So since mu 0 and mu 1 are 0, now what will happen? Okay. So now I will have this term, x square term will be there. But since mu 0 and mu 1 are 0, this term will go off. This term will go off. This term will go off. Right? These terms will go off. Correct? So now, in that case, HB equal to 0 if half x square into 1 over sigma 1 square minus 1 over naught square minus ln of is greater than 0. Okay. Now in this case, now again without loss of generality, assuming x square is ln of that means that this is a quadratic case. Now how it will look like? Okay, that's what the next code is about. This is how your data will look like. Okay, since you have a square, so then you take the square root of it, so you will have the plus and minus. Now this is how it look like, the boundary. Okay, we can simulate them. These things can be simulated quite easily. Okay, so again a couple of small things. Self-help. Help yourself with self-help. Try the same thing out. Try out for x belongs to Rd. Okay, now what do I mean by that? Now this is P of x given y is equal to I is from some normal distribution, now wherein which it is having mu I and sigma I, which x belongs to Rd. Okay, now this is the case that I am trying you to look at it. Now look at this and convince yourself that you get similar kinds of results. Okay, so now let's see how is the error. Okay, now we were always looking at the risk. Now let's put some value, how it will look like. Can we this is the last step. Can we actually obtain some computable values? Okay, now we will do it explicitly for a 2 class m is equal to 2 case. Okay, and then assuming 0 1 loss. Okay, so now consider the case of base classifier with 0 1 loss and m is equal to 2. This is the case that I am assuming. Okay, then we know that the risk in this case integral over RD. I'm assuming that X belongs to RD. It's fine. We have computed this. This is minimum of Y is equal to 0. To that X given 0 is equal to 1. This we have already computed in our earlier sessions. Now we have computed these cases. Okay. So now let's bring them to specific case. Okay. Now let's take a specific case where my X belongs to R. Okay. It doesn't matter whether it is an RD. Okay. And then the priors Y is equal to 0 is equal to Y is equal to 1 is half. And then the class conditionals X given Y is equal to I are Gaussian distributions. Now, when I say Gaussian, even put certain conditions is equal to U1 is equal to mu. Sorry, sigma 0 is equal to sigma 1 is equal to sigma. Okay, and then without loss of generality, I'm assuming that mu naught is than mu 1. So, in this case, so what will happen is now in all these cases, HB is equal to 0 if X is less than mu naught plus mu 1 by 2. Okay, now this will be my discriminant function. Now how will be my risk? Okay, now in this case, the risk that is obtained is the prior into minus infinity to mu naught plus mu 1 by 2 into X given Y is equal to 1. This is capital X. Okay, into dx. So sorry, I'm abusing notations left, right, center. Okay, now I presume that you can get them comfortably. Okay, plus 0.5 mu naught plus mu 1 by 2 till infinity is given is equal to 0 dx. Now this you can easily substitute and put them in the form of the standard normal table. This is phi of mu naught minus mu 1 by 2 sigma plus 0.5 into 1 minus mu naught by 2. This will be the error. Now if you explicitly, oh sorry, there is a 2 sigma here. Okay. Now if you can explicitly have the values of the mu naught, mu 1 and sigma, we can actually get the risk that is incurred. Now this is just to show that okay, these things are doable. Okay. Now with this we conclude our long tutorial on looking at the risk and then specifically looking at the cases in a much more broad and generic way and taking into consideration all the what do you call different cases wherein which we looked at even the outcomes can be different, and then how do you model the whole system in that case, and then when you take special considerations how things will be converted into the forms that we know in real time, like a linear discriminant, quadratic discriminant and stuff. Okay, I hope this was interesting and then you learned a lot of things. Thank you.